So the question says, examine this expression using the cis notation, polar. And it also tells us that the modulus of z is 1. So when we can just write z equals cis theta, we don't need to bother with an r or anything like that. So we realize that this is de Moivre's theorem. So we write 1 over z as z to the minus 1. And we therefore use de Moivre's theorem and we put the negative in there. Now, cis can be written cos theta plus I sine theta, so I do that for both of them. Remember that cos is an even function and sine is an odd function. And so the minus sign only survives there. And that means these I sines will cancel and we'll get 2 cos theta. Really nice. And the question says, let's extend it into this. Well, it's actually literally identical. And so we can say that z to the n plus 1 over z to the n is 2 cos n theta. It's a real number. Really nice. Then the question seems to change tack and ask you to use the binomial expansion to expand that. So we do that. That's very standard. I tidy it up. And then I'm just going to group them so that I get the z cubed with the 1 over z cubed. So this is just an identical line, but I've grouped them because that's the theme of the question. So then the question asks us to put that all together. Well, I know that z plus 1 over z cubed is equal to this, but I've previously proven that. So I can replace all of these with 2 cos n theta. In this case and this case, it's just 1. And in this case, it's 3. So I just simply replace it there. So for example, z cubed plus 1 over z cubed is just 2 times cos 3 theta. And I have this on the left-hand side, which I'm going to multiply out, 8 cos cubed theta. And it means we end up with an expression for cos cubed theta in terms of cos theta and cos 3 theta, which means we could integrate cos cubed theta. There's better ways of integrating cos cubed theta. How would you do it? Well, I would split it into cos theta and cos squared theta, turn cos squared into 1 minus sine squared, and make the substitution u equals cos theta. Really nice. Although this substitution means you can write down the answer to the integration, but it took quite a bit of work to get there. There you go.